Okay, as promised, then I would start with the fish story. And I think I will just do like this, so that we can have the fish story here. We have the different levels up here of which kind of treatment we have, and we have the blocks down here. And then you can say the question is basically just to investigate treatments of blocks if they have any influence on the regeneration of the seaweed. It's important to notice that these numbers are in percent. We'll get back to that in a moment. And then there's a question about interactions and stuff like that. But let's just keep... Oh, I had freeze off. Let's keep this over there and then swap to R here. So let me just, now I'm not sure I'm in the right folder. I was not. So let me go to session. So the fish contains the cover numbers here. Luckily, they're all between 0 and 100 since they're percentages. We have the block numbers. We have 12 observations in each block, and we have 16 observations for each treatment. So that is as we would like things to be. We were asked to do some plots first. If we just plot the fish, it will do a pairs plot per default. Let me just zoom into that one. So what do we see here? The first thing to notice is we have this nice square here. So the design of this experiment was a full factorial trying all combinations. So that's nice. You could say, if you were interested in other things, you may want to cut down things like that, but that's kind of the design of experiment approach to things. I won't dig into that. I'll mostly just treat it as a model. And then at the top row and left column, there you have how is the cover depending on the levels of the block and the levels of the treatment. But it's not so easy to see what actually happens here. So there are many ways of doing this. This is I should probably just change the margins a little bit here. Oops, that should be a comma. And then so what do I have here? I have the mean value for each of the treatments, and then the colored bars here are the various blocks. So here's just the mean value in every combination. Is it informative? To some extent, but it's also a lot of information. So it's not quite difficult to see what actually happens. But the one thing to notice is that this combination where everything is allowed, so whenever the letter is there, it means that that kind of fish or limpet is allowed. That's why you have the least regeneration, whereas in the control, that's why you have the most. Not surprisingly. And then you see in the first two blocks here, there you have a lower regeneration, whereas in the third and fourth, you have a higher. Another way would be to do a box plot. In this case, first for the blocks. And you can also here, you can easily see that block 3 and 4 are fairly large. Second, for the treatments, you can see the same patterns here. But what you don't notice so easily here is, well, I would go back to the block plot here. These all span from the minimum pretty much value and then to various maximums. So what is happening here is that within each block here is masking all the different levels of the treatment. So you have treatment that gives you small values and other treatments that give you high values. So the span of this is not actually that informative. you cannot see the interaction that, or the effect of the both of them here. So be a little bit careful out there. So in order to answer the question about interactions and things, one thing is to say, what is the appropriate thing to do? What we saw from the presentation today already is that if you do one variable at a time, you may not always see what is actually significant when you control for other things. So when you're asked to say if there's an effect of something, then you should also kind of take the other things into account. So before you answer any questions, it's fine to do the descriptive statistics like the box plot. But before you say anything about inference, make sure you make a good large model and then you use one model to answer all questions. At least almost all questions. But for the main questions, figure out what is the best model. So we're looking at the cover and interaction between treatment and fish. Let's look at the ANCOVA. And we see that everything here is highly significant. Also the interaction. So let's look at the summary here. This is one of the messiest lists that I can show you. Is this actually informative? Well, the one thing to notice is that there's a lot of combinations here that are not significantly different from the reference. So maybe we are using too many parameters here. But before doing too much inference, let's just do a diagnostic plot of this. So what is your immediate comment here? That's one thing to notice. The plot down here is different. So now you have the factor levels of the treatment, and you see the various standardized residuals in each of those. Nothing is near Cook's distance, then I think it will pop up. So when everything is balanced, you'll see this, because when you have this balanced experiment, every observation has the same leverage. Every observation has the same influence on the parameters. So therefore, if you do the traditional plot, instead of having the factor plot here, it will just be all the points being on one value for leverage, and then you'll just see basically all these points here merge into one x value, which is not informative. So what is your conclusion here? There's something that is not as we want it to be. Yes?
If we look at the residuals, we can actually see that the variance increases and then decreases after some time. And this is what we see in the scale plot. The variation increases and decreases again, so we need to transform the response.
Yes, that will be very appropriate. Now, I will add one thing, and I won't start with the most optimal thing, but I will start with the most logical thing to do. So typically, if you see something like this, you could just try, should I use a square root, should I use a logarithm? That's what I've done so far. But today I will do something slightly different. I will look into the mass library, that's from a different book. And then I will do what is called a Boxcox plot. Now, the interesting region here is somewhere between 0 and 1, so I'll just redo it in a different interval just so that we can zoom in a little bit. So what is the Boxcox transformation? What we heard is that we need to consider transforming the response. So what we do here is a so-called power transformation. So you take the response, you raise it to the lambda power, subtract 1, and divide it by lambda. That's the Boxcox transformation. This minus 1 and divided by lambda, basically we're just raising to a power. But adding this minus 1 and dividing by lambda, that means that even if lambda is 0, we don't like dividing by 0, but in case, so this is what it is when lambda is different from 0, and it's a logarithm of y when lambda is equal to 0. So this is just to make sure that it has the logarithm as a kind of continuous thing in there. So what we see here is we're trying to maximize the likelihood. I haven't said much about likelihood, something more about it. The likelihood is basically saying what is the likelihood of observing what we're seeing under different transformations, and then you can see we want a maximum likelihood to find the power that gives us the maximum. And then what is listed up there is that you subtract a particular number that corresponds to where the likelihood crosses that, gives you 95% confidence interval for what the optimal lambda is. So what I suggest that you do in practice is that you look at, well, which value do you get? In this case, close to a quarter. It doesn't have to be exact, it just has to be a number in the ballpark. It's not 0, it's not a half, so a half is the square root. And 1 is doing nothing, so that was what we started out doing. So that's not at all possible, optimal. But using a quarter, typically use some fraction that is meaningful. Half, a quarter, a third, or the log. That's kind of the usual suspects. So if I do the same model, where I use cover raised to 1/4, again, this small add-on out here is just to make it a continuous thing for the logarithm. But now we just need the power transformation. The other thing is just an additive thing, so let's just do it like this. And let's look at the diagnostic plot again. I should probably change the... we can read it as is, I guess. So, is this better than before? I would say the QQ plot, which is what has been optimized, is much nicer than what we had before. But is it the way we want it to be? We had a problem initially with the variance here in the beginning being much smaller than what you had later on. That's better, right? But we see another thing is now that when you get to high fitted value, the variance starts to decrease again. Bummer, to some extent. We would have wanted this to be a horizontal line, and often that's what you would get, but we had to think back. What are the data that we have here? We have percentages. And I know it's a long time ago that it was Tuesday, at least mentally, but the variance of a binomial distribution n times p times 1 minus p. So for a given n, we cannot change the number of elements in here. What is the shape of this? It looks like that. Goes to 0 and 1, oh, and in 0. So how does that look compared to what we have up there? So rather than doing this transformation, maybe we should do a transformation that can help us with this. Something that helps us with inflating the variance to small values and also inflating the variance when you get close to 1. And decreasing the variance in between. That's the way. So what do we need? We need a function that helps us there. There's one function called the logit. It's defined as the log of p divided by 1 minus p. That's what you use. Now, this is outside the scope of this course. In a generalized linear model, which is the GLM function in R, not the LM but that we're using, there, if you have a binomial response, then you use the logit transform as the so-called link function. So you transform things and do things in that space. We can do that here as well. So what I will do is that I will create a new column called logit cover. That is the cover divided by 100 to get it a proportion rather than a percent in numbers. basically just calculating that. And then I'll use that as my response and plot this again. Now look at the scale location plot again, lower left corner there. It's much nicer, right? The QQ plot is still quite good. So, and there's no really anything that depends on the levels of the treatment. If I wanted to be the blocks instead, then I could just swap the order. So what happens here? It's the one that the first factor up here, that's the one that is being used in the lower right corner to explain things. If I want to show the block as well, I can treat a little bit here and say that the color of the points should be as.numeric of fish $block. Then it gets, hopefully it gets just messy. Because now we can see that we have the blocks for different colors in here. There's one thing you will notice though, if you look a little bit careful. I don't know if you can see it. You can see it down here. Only in this plot, that's why you can see it. Every color has exactly 2 observations. We have a full factorial model. We have all combinations in the model. So therefore, and we have 2 measurements in every combination. So what we see here is that we have all observational distributed blue ones. They are pairs. So we have always a positive and negative residual with the same numerical value, because you have 2 observations in each combination. Does that make sense? I see some faces that are not totally smiling clear. So because we have 2, we have in this model 6 by 8 parameters that we estimate. For each combination of parameters, we have an estimate similar to this one of what is the mean value in each group. And the mean value in each group is the mean of the 2 observations that are made in that group. And of course, if you make the calculation of the mean value of 2 points, then you would have one that is above and one that is below equally much. So that's why you have that mirrored pattern down here. But it's fine, it's expected, and it's okay. So now we can go back and look at the ANCOVA. Before everything was significant, but actually now the treatment is not, the interaction is no longer significant. So let's remove the interaction. Let's plot the model again. It's still okay, at least still not worse than what it was there originally. The lower scale location, it seems a little bit of tendency to a larger variance, but not too much. We do the ANCOVA again, but in order to see if we should remove something, what I did was to remove the last parameter. But what we should do would be to use the drop 1 to see if the first one is also relevant to remove. And we see that they are both highly significant. Now the summary is now quite a bit shorter than what it was before. We have the reference level that is block 1 and the control, and then we see how is the difference for all the others relative to that in the logit domain. And we also see that pretty much everything is different from the reference. So no surprise that we have a significant levels here. But it also means that the effect of the different treatments is independent for the different blocks. Now, this was what you could do. And it is one of the things where, depending on the transformation, you end up with different models. If you did not transform, you had the full model, but here after transformation, you actually reduce to a much simpler model, where you say that the treatment effect is the same everywhere. So if we look at the model up here, and if you look at the parameters down here, then what we notice is that all those, the last 3 treatments down here, let me just try to highlight them. They are having the largest effects. They're somewhat different, but they're much greater effects here than you have for those where the limpets are not able to access the sites. So what we could do is ask the question, is just limpets doing it all? And then one way to do that is to create a new treatment as a copy of the previous one, to say the levels here are, I'll just combine those with limpets in here. I'll fit the same model as before, and I will compare the 2 models. And then I'll notice that there's a significant difference, so that means I should not have merged those 2 levels. I should keep the complicated model. Now, if you look at the description of the blocks up here, block 1 and 2 are the same exposure, same zone, namely just below high tide level. And then you have exposed and protected. Then you have a mid-tide that is exposed and protected. And then you have just above low tide, exposed and protected. And then you have on a near vertical rock wall. And then you have, you can say, different tide levels here that also to some extent corresponds to the level of protection. So you have the blocks where you effectively have a zone and then a protection level. So I will recode the data to give you an exposure and a zone variable. So now I have everything that was there before, but now I add, instead of having an 8-level block, I have 1 level for exposure and 1 level for zone. You may say, from a design of experiment blocking kind of view, don't play with this stuff. You want to, if you have sufficient number of observations, just keep the blocks there. Don't split it down. But now I'll just do it just to show things, just to play around. So I will take the treatment, and then I'll take the interaction between zone and exposure. That is the same model as before. And just to prove that, I will compare it with the model from before. And the degrees of freedom, there's no difference. The residual sum of square is also the same, so there is no difference. It is the same model. And then I'll compare with the model where I remove the interaction between the zone and exposure, and compare those 2 models, and it's not significant. So if I'm just doing the ANCOVA style without thinking too much about what was the background for the data, then you should use the simpler model. So the one without interaction. So now we're down to this model. This could be a good place to start. Or stop, sorry. But there's one more thing. When we look at the treatments here, what is it actually that we're looking at? We're looking at 3 different treatments, effectively. We have limpets, we have small fish, and we have big fish. How many combinations are there of on and off of 3? Well, 2 to the 3rd power, I can do that, that's 8. But there are only 6 levels there. What is happening? You cannot allow big fish without also allowing small fish. So there are 2 combinations that are not in the list, namely just big fish, as in just an uppercase F, and limpets and big fish. Those 2 options are not physically possible to make, but nevertheless, we could try to make additional factor for the treatment to have on and off for, if there is an uppercase, what I do is I test for each observation, is there an uppercase F in the treatment? Then I get true and false, and I treat that as factors for the large fish, for the small fish, and for the limpets. So now I have extra columns out here. And now I'll make a model. Again, I will do the interactions between all those three. That gives me the same 6 levels, and actually 2 more that I'm not going to have any observations in. And then it gives me the 8 combinations out there. Here I'll do the step. I won't look at what it did because that's just a lot of... But what I will do is to look at drop 1, to look at if what is left is significant and I cannot reduce the model. So let me look at what the model actually is now. It's saying that the treatments here are actually independent. It's the effect of each kind of fish is independent of the others. Likewise, the zone and exposure is also. So now we can actually look at the summary of this model. And we again have a fairly, even smaller model describing this data set. And all parameters are also significantly different from their reference values. Now, when you do step, you may sometimes run into the problem, not just with step, whenever you want to estimate a model. In this case, it's not a problem, but in other cases, you may have actually more parameters in the model than you have observations. I think many of us have been there, that we want to know more than what is out there. That's basically what it is. So what you can do is you can take a model. It can be a small model, a big model, doesn't matter as such. And then you can do, instead of just using step to reduce the model, it's called backward selection. You can also do forward selection. But you can also do what's called stepwise selection. So what I do is that I define a scope that is the product of everything. So that's a model with all the interactions. So that model is effectively the initial model, actually a little bit larger, because I have 8 combinations of the treatments where originally I only had 6. If I do this instead, so I'm allowing, 5-way interactions. Some of them, let's hope that we get a reduced model by running this. First, let's just look at how is the model looking. The first thing to notice is now that we've only had some weird interactions. Not all observations have the same leverage. So now we don't get the factor levels anymore. We get the traditional levels plot. But they're all quite similar in importance. And all the rest is similar to before. The variance is a little bit lower for small fitted values, but not too much. We should do a drop 1 of A9 test equals F. Actually, why didn't I do this before? So basically, I have too many parameters in the model still. I have a lot of different things in here, some interactions. So we should probably reduce our model by first removing the least significant one, that's zone and exposure. So now I will cheat a little bit in here and I will do things. I'll update A9. It's not actually cheating, it's just very compact. Take what is there, and then I will remove zone, colon, exposure with an extra P, like this. It will remove that parameter and do the test in one go. I still need to remove the TRF for the big fish and exposure. So rather than making a new model, I will just keep removing what I need to remove. Now what happened was that since exposure is no longer part of a higher order interaction, it also starts to look at removing exposure on its own, which is highly significant, but I still need to remove this one here. So I'll go up here and subtract that one as well. I should still remove the one with the limpets and zone. And now everything is significant. So let's look at what is A10. We're actually back to the model that we had just before. So this is the best model. And relative to the model that you made with 48 parameters, I find this a little bit nicer. It also took a little bit further time to get there. I'll give you that. But this is pretty much the task that you're going to do in the first exercise, the first case. That's along the lines of this. I will save this and upload this script so you have it. And I hope you understand why I didn't want you to present this. But I hope it gave you some insight. And I think using the Boxcox is one thing, and the other thing is looking at what is actually there. That is something different, but I wanted to just show you, establish your help, use drop 1 with test equals F to get the information that you want, rather than using these p-values out here in the LM or use the ANCOVA summary, use the drop 1 to progress. Now, the question is, should I have a break now? Should we have a break now and then continue, or should I just go head on into the lecture? Or what I presented. It's not a long lecture, but it's expanding on what we've done so far. So, anyone needs a 5-minute break, and then we'll make it a 5-minute break. I think it's good to have a 5-minute break. So let's make it sharp, 22 minutes past. Jeg får lige uploadet den her fil med det samme, så jeg ikke får glemt det. Det var ikke der, den ligger. Kan jeg forklare hvad?
Hvordan man korrekt til sidst tænker, når man laver en model, så vil man jo gerne præsentere den, så hvilken indflydelse har de forskellige.
Det sprang jeg lige over her til sidst. Ja.
Så tænker jeg, at det forklarer det på et tidspunkt, og så særligt når det er en transformeret variabel, eller transformeret respons, så skal man jo helst ikke plotte det transformerede respons, når man præsenterer modellen.
Jeg gør det i den næste, faktisk forelæsning i den del af det, men tak. Ja, jeg må sige, lige præcis i den her, der synes jeg, det er svært at præsentere det. Men så er det heller ikke værre. Men hvad er det?
Ikke fastholde, altså fastholder man ikke bare de andre variabler, så plotter dem i 2D en af gangen? Eller?
Det kan du godt gøre, men når du har så mange variabler, så bliver det noget lort, ikke? I den konkrete model.
Det er også det andet, det er det transformerede respons. Altså, så skal man inverse transformere begge sider, før man...
I den konkrete model, der tror jeg vil nok gøre det for... Vi har de 4 zoner, og vi har med og uden exposure. Ja. Og så har vi on and off med 3 treatments. Så hvad vil give mening at gøre her? Der tænker jeg, at man kan godt præsentere 8 tal ad gangen. 8 værdier i en graf. Med en usikkerhed på dem. Man skal også have usikkerhedsintervallerne med. 4 zoner og plus minus exposure. Så viser hvad er effekten af dem. Og så kan man jo gøre for hver kombination af de her treatments. Så jeg vil nok lave 6 x 8 på en eller anden måde. For at kommunikere det. Men egentlig kan du gå tilbage og tage dit barplot fra starten af, og så vise dem. Det bliver bare så voldsomt. Men problemet er, når du så har de her treatments, skal du så kigge på dem hver for sig? Eller skal man kigge på dem i alle kombinationer? Og det er der, hvor det bliver svært.
Næsten nemmere bare at kigge på tallene. Altså,
det er næsten nemmere bare at kigge på tallene, ja.
Lave noget graf, ja. Når det bliver så stort.
Ja. Fordi det effektivt er 5 faktorer tilbage, så er det meget, meget, meget svært. Jeg kan lave jeg har nogle tegn. Hvis det lige er en mindre, så giver det mening.
Men det er sådan set, altså det er jo interessant nok bare at præsentere en tabel, hvor man siger, bare, altså, hvor man siger, det er de her parametre, der har en signifikant indflydelse på. Altså dem, vi skal holde øje med. Man har bare altid lyst til at lave form for...
Ja. Jeg har faktisk en graf. Jeg har en kode, der laver med fine bar for error bar og sådan noget, også på alle estimater og sådan noget. Ja. Den regner jeg med at dele på mandag.
Det vil være fedt.
For dem får I brug for mandag.
Ja. Det er godt med for nogle gode ting, ja.
Men den er rigtig svær, den her. Og fuldstændig enig.
Jeg kan i hvert fald ikke sådan lige...
Og der vil jeg sige, der går det igen tilbage til, hvad er det for nogle spørgsmål, du stillede til at starte med? Fordi det nemme vil jo være at sige, jamen okay, vi ser, at der er ikke nogen interaktioner, så vi kan nøjes med at gøre det for en zone.
Altså man kan altid simple analysen ved at stille et simplere spørgsmål, men det, jeg tænker bare tit, at når man laver sådan et forsøg, så vil man jo tit tage ting med i sit studie, som man aner egentlig ikke, om der er noget.
Nej, præcis.
Og så tænker jeg, at man kan jo næsten ikke lade være med at teste for alle interaktioner, hvis man har observationer nok til at gøre det. Så,
men vi er faktisk igen med en ret simpel model, uden interaktioner overhovedet.
Ja, det vil man jo faktisk ret tit gøre, tror jeg.
Nej.
Gør man ikke det?
Nej, der er ingen interaktioner.
Det ved jeg ikke.
Her, jeg har faktisk, hvis jeg kigger på det her forsøg, her er det limpets, der spiser mest, ikke? Den giver den største reduktion. Limpets true giver minus 1,8, hvor de andre giver minus 0,4 og 0,6, ikke? Ja. Hvis nu limpets i forvejen har, kan man sige, 1, så er der jo mindre tilbage til de andre fisk at spise. Ja. Så derfor har jeg faktisk forventet, der vil være, men der er åbenbart nok tilbage til det stadigvæk.
Okay, ja. Sådan at de andre afhænger af den første.
Ja. Men her, de kan faktisk blive ved med at spise på samme måde, selvom de andre har spist. Ja.
Jeg har altid tænkt på det, som at man egentlig forventer, at der højst er sådan to faktorer interaktioner.
Ja, men der er heller ikke nogen interaktion.
Tilfælde, hvor der vil være noget over det, sådan når man generelt lægger ting.
Ja, men igen, det afhænger meget af, hvad er det for en konstruktion, du laver.
Jeg kan godt se her, så vil man næsten forvente, at...
Men der er ikke nogen interaktioner her, vel? So starting with a comment, was a good question coming here. How do I present this model? How do you present the results from this? That's not just straightforward. First of all, it's a transformed space. So most people do not, you can say, live in a locked space. It's not a natural space to kind of think of. It's a bound space in the outcome, but in the parameter space, it's from minus infinity to infinity. So what to do about this? There are many ways of presenting this. What I would probably suggest would be to make some kind of a bar plot with some error bars on top for those combinations that you find are the most relevant. In the particular case, there are no interactions. So you could probably say, well, what is the most interesting thing? That's probably to say that we have the different treatments. What is the effect of that treatment when you look at the proportion of regenerating seaweed? So if you say pick a zone and then say with or without exposure, then you can make a nice plot for that combination. And then you can do the same thing for the different zones. If you like, I'll try to make a plot that does that, but I won't just do that here while you're sitting watching me, because that is one of the things that is a little bit complicated to code so that it looks like nice. What I would do is to use the predict function to create a prediction interval or confidence interval, depending on what I want. Probably confidence interval, not to have too much uncertainty. And then have some bars for the different combinations that I choose to include, and then add these error bars on top. That's what I would be aiming at. Yes?
You reiterate when it's the
that's a matter of, are you going to say something, how confident are you about the expected mean value, or are you looking into, if I repeat the experiment, where do I expect to get observations? So here, what you would probably say is, I'm not going to repeat it, but I want to know what is the expected, what is the uncertainty on the expectation of the value there. So it's a matter of whether you take the uncertainty that comes from the epsilon into account or not. Do you add the uncertainty that comes from the measurement error, or do you just want to look at what the model predicts and how certain is the prediction? So if you just do the confidence interval, basically what you can see is, well, are they actually different? Then you get a much clearer view of that. Whereas if you add the measurement error, then you have much more overlap. Not because they're not different, but just because you add the measurement noise. But whenever you have repeated measurements in a group, then you can say, then you reduce, then you increase the information and you can prove smaller differences. So I would often pick one or the other, but again, it depends on what is the interest. Is the interest on the expected value, or is the interest in which outcome to expect? Is that along the lines? So we're going to do a general linear model, which is basically also called ANCOVA, analysis of covariance. And just to do a quick recap, the other day we were looking at linear regression models of this sort, just to do the simple one as an example. Then yesterday we looked at analysis of variance. Yes?
You uploaded the wrong slides from the time series.
I'll do that later, thank you. I was a bit too quick. I only did it this morning while you were presenting, and I did not open the file before. Okay, whatever. But what we are going to do today is to say, what if you have the combination? So we have different levels here. Then we have something that is a continuous variable here. And then the beta here, which is the slope, may also depend on the combination of a factor level. So what does this model represent? Say, if k is equal to 2, that means that the factor has two levels. There's only one factor, same factor that codes for alpha and beta. What does it predict? What does it describe, this kind of model? I'll show you. Two slopes and two intercepts. Because this is the outcome, I just simulated some data from two groups. So we have a two-level factor, that's just the color here. We call them A and B. And then each group has its own intercept and each group has its own slope. So I can fit that model. And here I have the prediction interval for this model. And what does this model look like? It's quite similar to what you looked at for the ANOVA tables, with interactions and other things here. But what is the interpretation of this here? What was the model that I used to simulate here? Can you guess that? You have a factor 1. The factor is called f1, and the continuous variable is called x1. So if you look at this, this value here is quite close to 1, right? So you have the expected value here is, if the factor here is a, for the A level, that is just the intercept. So we have an intercept of roughly 1. Now, if you change the factor to B, what happens then? This is the same thing as for the ANCOVA model. Then you have to look at the factor for the other level there. Well, I have to add 2. So how should I write this? So this is, let me write it like this. 1 plus 2. This is for A. And this is for B down here. So those are the intercepts. And then I have something times x here. I have one slope here that is roughly 0.5. What is the slope for the other one? That's a question for you guys. Yes? Nope. Not minus 2.2 point, because you forgot one thing. Yes?
Yeah, you need to add the half.
Exactly. So it's 0.5 minus 0.3, roughly, right? Does that make sense? So in this case, I have 2 models where I have different intercept and different slopes. In a different model, in this case, everything is significant. I simulated to be that. But you could have had a model where the slopes were the same, but the intercepts were different. That would also make sense, right? So you have all various combinations of different intercepts, different slopes, whatnot. You can do everything you like in this kind of models. So how do you write this? I don't know if you recall the design matrix that we did the other day. How is the design matrix X looking like? What we have here is the alpha 1 level. The second one is the slope. That's a slope of beta 1. And then what we have, the F1B, that is alpha 2 minus alpha 1, just as we did the other day. And then the last parameter that we estimate there, that is beta 2 minus beta 1. So again, I have a column of 1s here. Here I have a column of my xi's down to xn. Then I have something that is a binary here. So I have sometimes 0 and sometimes 1 here. And in the last column, I again have sometimes 0 and sometimes the corresponding x. But only if I have the right factor level. Then I have something, otherwise it's a 0. Does that make sense? I see a lot of you nodding. It's not that you need to do this, but it's just to understand what is the parameterization of the parameters of the model in this case. Now, what I want to do is to go through 2 different cases. Also, going back to when I have this, in particular when it's on a transform scale, don't show the predictions on the transform scale, show them transform back, or at least do both. So I have some cells here that has been measured how they're growing at different cell concentrations and with and without glucose. So let's just take the data. It's the wrong folder. It's like this, but the glucose here is actually a factor, 1 and 2. I will make it a factor with labels yes and no, because that makes life easier to understand later on. So I have the glucose level, I have a concentration here, and then I have the measured diameter. So these are inputs, predictors, and then we have the outcome. Let's do a pairs plot again just to see what we're looking at. And you can see the immediate conclusion is that, well, the two-level factor kind of is not that informative, but we can definitely see that there is a relationship between the concentration and the diameter, but it's definitely not linear. So we need to consider transformations before doing anything. We could, just for the fun of it, say we did not observe that, just fit a model. I actually don't want to look at the summary. It's not meaningful. And just plot the residuals for this model. And we see that there is some curvature here. The QQ plot is not too nice. We have an observation that is far out. But we should not have done this because we knew already that we need to make a transformation just by visual inspection of the data. So what I'll just try here, just to do the log transformation of both the concentration and diameter, and look at the pairs plot again, and then see, well, is there something somewhere where we actually get a linear relation that is of interest? Where do we see the best linearity? You could say you see that in the log diameter and the diameter, it's almost linear there because of the scale of the log. But if you look at the diameter, here is the response that we want to predict. Then the log concentration and diameter, when we also keep in mind that we have different glucose levels, that's probably not too bad. So let's try a model with the diameter and log glucose. Just to show you, you can also, if you like to write all the interactions yourself, you can also just write them like this. It's the same model. Let's look at an ANCOVA table, remembering that the last p-value is credible, so we can see that the interaction here between log concentration and glucose is not significant. So that means that what we have here is that this interaction, what does that code for? Between a factor level and a continuous variable. What is that factor explaining? Do we have, in this model, it's exactly the same structure as what we had here. Different, a factor, we have a combination of a factor and a continuous variable with all interactions. That is the model that we have here. So if the interaction between the factor and the numeric variable is not significant, what does that mean? Yes? You have parallel, you have the same slope exactly. So in this case, let's try that model. Let's do an ANCOVA. Let's do a drop run instead. And an F test of that. Everything is highly significant. Let's look at the diagnostic plot. The QQ plot is still not perfect, but all the other plots are much nicer, and we don't have anything that is sticking out as extreme observations anymore. So that's another thing when you have a transformation that actually allows things to behave nice. That's not a bad sign. Let's just look at a summary again of this model. So what we have here in the log, we have the log of the concentration, and then we have the reference is glucose, yes. If we remove it, we reduce the outcome. If we want to plot this, first just plotting the data, showing with the cutter, with and without glucose, looking at the coefficients, what is that we need to draw? Well, for the first group, we need the intercept as intercept for an AB line, and then the slope is just the second coefficient. So I take the first and second coefficients, and I add that line. Now to do the other one, what I have to do is I take the sum of the first and the last coefficient, so everything but the second coefficient. Maybe it's easier to read if I write 1, 3. So that's a prediction for the other one. This is the manual way of doing it. When you only have this few number of parameters, it's doable, but in practice you want to do it with using predict. So what I do is I make a data frame, in this case, where I repeat some concentrations, and I want to have each of them twice. That's what the rep here does. And then the glucose is just yes, no. So what I get out, if I do the head of this, is that I get each concentration repeated twice, and then I have it, so I have it with yes and with no. Then I can predict on that data frame, same procedure as yesterday and the day before, and every year. So if I plot again, I should make this plot nicer. Have the diameter tilde L conc, and then it's from the hell. That's the name of the data frame, right? So that's just the same plot as before. And now what I will do is that I will make math line as before, where I just add first those with glucose, and then those without glucose. So those are my confidence intervals for this. And as we discussed this, here I use the natural log of the concentration. That may not be meaningful for everyone. Probably if you want to present it to someone, use log 10 instead. That's more meaningful to most people. But let's go back to the original scale, plotting the points as they are. Basically, the only thing I do is I take the exponential of the log concentration that I use to predict with. It looks like this. And if you also, that was the confidence interval, if I add a prediction interval as well, I get this. Quite a large number of lines, I know. And what you notice is that the confidence intervals are not at all overlapping, but the prediction intervals, they do overlap a little bit. Also illustrating, as was mentioned over here, that you can say when you want to show something for the, what is the model predicting, it's nice to look at the confidence interval. So that was one case. Now the other case is about so-called vital capacity, is how good you are breathing. It's from another book. The data set here, let's just look at a summary. We have 3 different groups, and they are defined as how many years they've worked in the cadmium industry in the UK, as I recall. And these groups, we should actually give them, it's a plus 10 years, 0 to 10 years, or not at all. That are the actual labels for this. So let's just code it as a factor and see what are that's the F group out there. So I have 20 individuals, 12 that were there for 10 plus years, 28 that were there between 0 and 10, and 44 that weren't there. Just to do a pairs plot to show what's in here, we actually already see here for the age and the vital capacity there is a reasonable linear relation, so we don't need, at least at first, to consider transformations. If we want to look at how are the groups different, just to show the observations separately, using a lattice plot here, there's one thing to notice here is that those that are in the 10 plus group, they have an age of at least 38 or 9. Whereas those that are not, they have a wider age span. And those that are in the 0 to 10 group, they also have a quite wide range span, but they're fewer for lower ages. Quite obvious, but it's important to keep in mind. So what we'll do is we'll fit a model where we have age in combination with the 3-level factor. And we just do the ANCOVA first. We could do the drop 1. The conclusion will be the same, namely that the interaction here is significant. So that means that the different groups, as the different periods they've worked in the capital industry, has a significant impact, and they have different intercept and different slopes. If you look at the summary, this is what it looks like. The slope for those that worked there for a short time is not significantly different from the slope for the reference group, but it is for those that worked there. No, sorry, for the reference group is 10 years, but those that did not work there, they have a significantly different slope from the reference group. So that's what we have. You could consider relabeling this so that it's the not working that is the reference group. But again, we're only going to show you plots, so the actual order of the level doesn't matter. I won't communicate it through the table, but through some plots. First, just look at the diagnostic plot. Are we actually happy? Initially, we assumed that we did not need to transform. We say the QQ plot up here is reasonably nice. The scale location is reasonably nice. And the residual versus fitted is horizontal line. So at least I'm happy. That's one place to start. And just to see if you change the order, let's do the ANCOVA table again here to have it. I just changed the order so H becomes before F group. Just to show you that the order matters for the p-values here. For the p-value for F group, if you test it alone at first, it is significant, but if you first include H and then include, so you have first a linear slope and then include different intercepts, then including an intercept on top is not significantly different from just a common slope, a common line. It's only when you add the different slopes on top of different intercepts that you have significance. So this is just to show you that it's dangerous to just look at an ANCOVA table. What you should do is to look at drop 1 of, now I forgot what the model was called, LM1, test equals F, and it only encourages us to look at the interaction, which is also in both models up here the same p-value because it's the same interaction comparing the same model. So that means we have a full model. We just need to do a plot. Let's plot the data. What I've done is that I've color-coded the points according to the age, how many years they worked in the cabinet industry. Let's look at the coefficients here. If we do it manually, basically what we have to do is to keep track of what is the intercept and slope for each group. Just like before, the reference group is just the first intercept here and the slope from H here, which is the fourth coefficient. Now if you go to the second group, then you need to add this to the intercept and you need to add this parameter down here to the slope. And for the last group, you have to add this to the intercept and that to the slope. So this is what we have. So what do we see here is that the black line represent those that were there in 10 plus years. So basically what we see is, now I'm cheating a little bit. So if you look at it, just look at the lines there and ignoring the dots for a second. Basically, if you haven't worked, then you have the lowest vital capacity. It's a physical strenuous work, so therefore it makes somewhat sense. Up to a certain age, and then those that work there for a shorter time has lower vital capacity, and then the old one that's worked there for a long time are the ones having the least vital capacity. But the one that worked there for a long time I mean, if they were 20 years today, of course you cannot have worked there for a long time and be 20 years today, but they'll be. So this prediction is one of those that does not make too much sense for the black line when you get below a certain age, because you need to have worked there for 10 years in order to be in the black group. But even though for the younger one in the black group, they are actually having better performance than some of the other groups, if you just look at the lines. But now we should also take everything with a grain of salt. So what I will do is I'll do expand.grid, gives me all combinations of ages here, step by 2, and all groups here. Let me just look at the head of data. So here you see the ages coming, stepping 2, and then you see a vector of all the ages for each of the groups, just like before. I'll do the prediction. I'll do the confidence interval. I won't look at it. What I will do is to combine my prediction data and my prediction intervals and look at the beginning of that. So I have my fit and lower and upper as my third, fourth, and fifth column. And then I have my grouping here. So let me just clear the plot. I want to know all the, just have the levels there. Then I will make, this is a little bit complicated way of doing it. I could just write 3 lines that does it. But this works for any number of levels of the factor. So for each level, what I will do is that I will say which are the relevant predictions by looking in the data that I combined here for my predictions, which has the relevant level. And then I will use mat lines to plot that particular one, like this. It's a bit busy, I'll give you that. So maybe I should have line width here to be 3,2,2, and then just redo the plot, so that the expected lines are a bit thicker than the other lines. And I should of course add a legend. I'll just copy it from before. Before including it, I'll just make the plot a little bit larger. So here you can also see that for the black line, when you look at potentially young persons in that here, actually the uncertainty is quite large because there's no observations there. You only have observations in the plus 10-year group for high values. So that's why you have, you can say, the most narrow confidence interval. And you have fewer in this group, so the black interval is wider than the green interval, representing those that did not work in the capital industry. So things are somewhat behaving as expected. So this is the kind of models where you combine everything. Of course, you can also consider all sorts of transformations and other things. Keep in mind one thing as well that I did not mention sufficiently number of times. That is, if you transform the response, you cannot compare them two models with different transformations, because it's not the same observations that you have. Likewise, if you remove an outlier, you cannot compare the p-values or ANCOVA between with and without an outlier, because it's not the same observation. You remove the most extreme observation, most likely. So that means you got a large reduction in the estimate of variance, and therefore, of course, it's something different. That also means whenever you do something like this, you should always step back to the initial model and start redoing your model development all the way through. Don't just take the last model that you got to and say, that everything is fine. Go back and repeat. Using step and drop one it doesn't take a long time. So do yourself that favor. That was what I wanted to say for now. What is left for the day is that after lunch, I will kind of say what is that I expect for the reports. It's just going to be a brief kind of overview of what is expected. I could also, and then the first case will be available at 3 o'clock. That means after 3 o'clock, I will be around and ask general questions if there's something that's not understood in the way things are formulated, so that if you're thinking of things over the weekend, at least you can get some things sorted out today. And if you have questions regarding that during the weekend, write them in Piazza. Then I will look at least sometimes, not 24/7, but I will be there. Just to try to see where does it bring you. And then on Monday, or all of next week, these were the groups. What I've done is I made another Google Sheet. I'll share the link later, where you can book a 15-minute slot. Each group can book 1 slot each day, nothing more. But you're allowed to talk with other groups. So if you have a friend group, I mean, it's a good idea to have one ask questions earlier and the other one a bit later. Because then you get more out of my time, but in this way, everyone gets the same amount of help. It's a matter for you guys how you use my time efficiently when I'm there. I'm not going anywhere, I'm with you for that 15 minutes. I just need to walk to somewhere else. Sorry?
15 minutes, Monday, then Tuesday, then Wednesday.
Yes.
So 45 minutes.
45 minutes in total for the first one, and for the second case, I will be, when I book myself in here, that's because I have to be at a meeting. And the Wednesday next week, I will give a short lecture introducing case 2, and then I'll go home and read, and read, and read, and read. And if I'm not done Thursday morning, I will get up and read, and then I'll get here when I get here. And then, so maybe the Thursday morning will be a little bit different, but I will make sure that I get around to everyone, and maybe just 10 minutes if I'm pushed too much. But in this way, everyone gets the same, because I've tried previously where some are very good at asking very detailed questions and try to kind of, as long as you can keep me sitting there. And I don't like just walking away trying to help people, but if we are on time, I think it's fair to everyone. So make sure when we get there that you write down the questions so you know how to use my time efficiently. It's a hard day for me, and you can look at, there are some 20-some slots there, so it pretty much needs that every slot has to be used. Otherwise, you're not getting help. So someone has to use the morning slots in order to get someone to get help. So if you do not book a time and all the remaining time slots on that day are gone, too bad. But I'll share the link later. It usually just works out fine, but it's basically just saying that I'm here the entire day except for a bit over 1 hour on Thursday and 1 hour Monday morning. Otherwise, I'm here all the time when you're working on assignments or I'm reading. So, but I save questions for that till the afternoon, when I'll give you what I expect as well. Any other questions? Otherwise, there are, in quotes, just 2 cases for now. But you can spend quite a bit of time on them. And there will be no more exercises for in the afternoon. It's just those 2 to look at those today to get a good feeling for how does this actually work in practice. Hitting some boundaries. Let me just check, did I cover everything? I think I got to say everything that was on my checklist for today. Okay. See you around at 1 o'clock. I mean, I'll be here as well for the next hour and go for lunch.